So this part deals with applications of correlation diagram method for explaining electrocyclic reaction and cycloaddition reaction. But before that, we must know some basic. So what is cone rotatory process or cone rotatory ring opening? The two atomic orbital components of sigma bond may both rotate in same direction, that is clockwise or anti-clockwise. So see here, this is positive overlapping. Okay, now if this orbital is rotate in this direction and this one in this direction, this is nothing but the clockwise direction. That means both orbital open in a clockwise direction. Then what happen? This positive sign is this one. Now this opens, that means positive sign comes here. Now you see positive, negative, negative, positive. That means in cone rotatory process, C2 axis of symmetry is maintained. Remember this point, this is most important. Positive sign, negative sign, negative sign, positive sign. That means what? This is not mirror plane symmetry, it is C2 axis of symmetry. So in cone rotatory process, C2 axis of symmetry is maintained. Then this rotatory process, the atomic orbital may rotate in opposite direction. That is, one in clockwise and other anti-clockwise. See here, this is positive, that means overlap. Now this orbital open in this direction, that is, this is anti-clockwise direction, and this orbital opens in a clockwise direction. Then what happen? This positive sign come off. This positive sign, it is like this. So positive sign is on upper side in both orbital. That means here mirror plane symmetry is maintained. So in this rotatory process, mirror plane symmetry is maintained, whereas in cone rotatory process, C2 axis of symmetry is maintained. Now, as you know, ground state and excited state. So both electron occupy position in the ground state, and this one is a excited state which is vacant. Now whenever light falls on this molecule, out of these two electrons, one electron is shifted to the excited state. So this is ground state and this one is a excited state. Now remember this point. If symmetry match in ground state, then that reaction is a thermal reaction. So if symmetry match in ground state, then it is treated as thermal process. Whereas if symmetry is maintained in excited state, then it is treated as photochemical process. So thermal process means symmetry match in ground state, whereas photochemical reaction means symmetry match in excited state. Remember this point. Now let us discuss application of correlation diagram method for electrocyclic reaction. As you know, as we discussed in the first part, this type of reaction is known as electrocyclic reaction. So we are going to discuss correlation diagram method for conversion of cyclobutene into butadiene or vice versa, and conversion of hexene to hexatriene or vice versa. Now let us discuss one by one. First, in this way, this is cyclobutene which is converted into butadiene. Now during this conversion, one sigma bond and one pi bond break from the cyclobutene, whereas there is formation of two pi bond in the butadiene. Friends, as you know, with one bond, two molecular orbitals are involved. For example, one sigma bond means sigma bonding and sigma anti-bonding molecular orbital. One pi bond means pi bonding and pi star anti-bonding molecular orbital. Whereas 2 pi bond means 2 bonding molecular orbital and 2 anti-bonding molecular orbital, which we describe as psi1, psi2, psi3, psi4. So psi1 and psi2 are the bonding molecular orbital, whereas psi3 and psi4 are the anti-bonding molecular orbital. Now see here, one sigma bond, that means sigma bonding and sigma anti-bonding molecular orbital. One pi bond, that means pi bonding and pi star anti-bonding molecular orbital. Whereas here there is formation of 2 pi bond, that means in this way psi1 psi2 2 bonding molecular orbital and psi3 psi4, that is 2 anti-bonding molecular orbital. This dashed line, that means below this line this is ground state and this one is the excited state. Now let us discuss sigma and sigma star. We already discussed the symmetry property of this molecular orbital in part 2, sigma bond. With respect to mirror plane symmetry, sigma is symmetric and sigma star is asymmetric. Okay. With respect to mirror plane symmetry, sigma is symmetric and sigma star is antisymmetric. Now pi and pi star. Pi, this one is pi star. With respect to mirror plane symmetry, you see here, if we place mirror here, then with respect to mirror plane symmetry, pi is symmetric, whereas pi star is asymmetric. So here, pi is symmetric and pi star is asymmetric. So these are the symmetric properties of molecular orbital, that is sigma, pi star and sigma star with respect to mirror plane. Now, there is formation of 2 pi bond. So let us discuss now symmetry of psi1, psi2, psi3, psi4. For butadiene, in this way, psi1, psi2, psi3, psi4. So psi1 is symmetric, psi2 is asymmetric, psi3 is symmetric and psi4 is asymmetric. So in this way here, psi1 is symmetric, psi2 is asymmetric, psi3 is symmetric and psi4 is asymmetric. Now see where symmetry match. So this is symmetry, then this is asymmetric, symmetric, and this is asymmetric. That means symmetry is maintained in the first excited state. That's why this process is photochemical process. Remember this point. Here symmetry is matched in first excited state. See whether symmetry is matching ground state. This is symmetric, but this one is symmetric, asymmetric. That means it is not match. So where it match? So symmetric, this is match. Asymmetric, this is match. And in this way, it is match in the excited state. So this is photochemical process. As I told you in basic, if symmetry is maintained in excited state, then that reaction is a photochemical reaction. So in this way, mirror plane symmetry, that is nothing but this rotatory process, as we discussed in the basic. Okay, so mirror plane symmetry, that is this rotatory process, is photochemically allowed. Now discuss if C2 symmetry is maintained, which is nothing but cone rotatory process, as we discussed in the basic of this part. Okay, how to remember? Cone rotatory C2. Okay, C. This rotatory means mirror plane. Now as we discuss, there is breaking of one sigma bond, that means 2 sigma orbitals are involved, sigma and sigma star. Then there is breaking of one pi bond, that means 2 pi orbitals are involved, pi and pi star. See here, one sigma bond and one pi bond. Now there is what happened? There is formation of 2 pi bond. 2 pi bond means 2 bonding and 2 anti-bonding pi orbital. So in this way, Psi1 and Psi2, these are 2 bonding molecular orbital. Psi3 and Psi4, these are the anti-bonding molecular orbital. Now symmetric properties along this C2 axis of symmetry that we already discussed in part 2. Now here I just summarize it on the page. Sigma and sigma star with respect to C2. Sigma and sigma star with respect to C2 axis of symmetry is symmetric and asymmetric. So here sigma is symmetric, sigma star is asymmetric. Then pi and pi star with respect to C2 axis of symmetry. So in this way this is pi and pi star with respect to C2 are symmetric, pi is asymmetric and pi star is symmetric. So here pi is asymmetric and pi star is symmetric. Now with respect to C2 axis of symmetry, Psi1, Psi2, Psi3 and Psi4. So in this way these are the symmetric properties of butadiene with respect to C2. Psi1 is asymmetric, Psi2 is symmetric, Psi3 is asymmetric and Psi4 is symmetric. That means asymmetric, symmetric, asymmetric, symmetric. So see here, asymmetric, symmetric, asymmetric, symmetric. So these are the symmetric properties of reactant and product with respect to C2 axis of symmetry. Now see where symmetry match. So see here asymmetric, asymmetric, symmetric, symmetric. That means here symmetry is match. In this way here also symmetry is match. So symmetry is match in a ground state. That's why this process is thermally allowed. If we wish to match symmetry in first excited state, then what happen? This is symmetric, asymmetric. That means this is not match. Though these two match, but this symmetry is not matched because this is symmetric and this is asymmetric. That means only possible thing is that symmetry is matched in the ground state. So in this way, if symmetry match in a ground state, then that process is thermally allowed. Whereas if symmetry is matched in the first excited state, then process is photochemically allowed. Now this is second example of electrocyclic reaction. Cyclohexadiene is converted into hexatriene. During this conversion what happens? There is breaking of the sigma bond. In this way that means there is ring opening, the sigma bond break, and there is breaking of these 2 pi bonds and thus formation of 3 pi bond. So in this way in reactant 1 sigma bond break, 2 pi bond break, whereas in product side there is formation of 3 pi bonds. So we have to concentrate on this now. 1 sigma bond, that means 2 sigma orbitals are involved, sigma bonding and sigma star anti-bonding. And 2 pi bond, that means there are 2 bonding orbitals and 2 pi anti-bonding molecular orbitals. Now here, since these are the 4 pi orbital, so we may treat it as Psi1, Psi2, Psi3, Psi4. That means we have to observe symmetry for Psi1, Psi2, Psi3 and Psi4 for pi1, pi2, pi2 star and pi1 star orbitals. Okay, now here there is formation of 3 pi bond. 3 pi bond means, as we discussed in the part 2, Psi1, Psi2, Psi3, Psi4, Psi5, Psi6. 3 pi bond means 3 bonding molecular orbital and 3 anti-bonding molecular orbital. Now let us discuss symmetric properties of these orbital with respect to mirror plane symmetry. Mirror plane symmetry means disrotatory process. If mirror plane of symmetry is maintained, then this process is a disrotatory process. Okay, disrotatory process means mirror plane symmetry. So this is mirror plane symmetry, that means disrotatory process. Okay, now whether thermally or photochemically allowed. Observe the symmetry. Sigma and sigma star with respect to mirror planes. So in this way, sigma and sigma star with respect to mirror plane symmetry. Sigma is symmetric, sigma star is asymmetric. So here sigma is symmetric and sigma star is asymmetric. Now psi1, psi2, psi3, psi4 with respect to mirror plane symmetry are. In this way, psi1 is symmetric with respect to mirror plane symmetry, psi2 is asymmetric, psi3 is symmetric, and psi4 is asymmetric. That means symmetric, asymmetric, symmetric, asymmetric. So here psi1 symmetric, asymmetric, symmetric and asymmetric. Okay, now let us discuss symmetry property of this hexatriangle with respect to mirror plane symmetry. Now psi1, psi2, psi3, psi4, psi5, psi6 with respect to mirror plane symmetry are psi1 symmetric, psi2 asymmetric, psi3 symmetric, psi4 asymmetric, psi5 symmetric and psi6 asymmetric. That means symmetric, asymmetric. So it is alternate symmetric, asymmetric, symmetric, asymmetric. So in this way, symmetric, asymmetric, symmetric, asymmetric, symmetric, asymmetric. Now see where symmetry match. So this is symmetric, symmetric in this way, asymmetric, asymmetric, symmetric, symmetric, then asymmetric, asymmetric, symmetric, symmetric, and asymmetric, asymmetric. So here symmetry is matched in the ground state. So symmetry match in the ground state, that means this reaction is thermally allowed. Now if I wish to match symmetry in the excited state, then see what happens. This is symmetric, symmetric, asymmetric, asymmetric. That means though these two match, what happens here? These two are also matched, but this matching is not possible. Symmetric or symmetric. That means here possibility is only that symmetry match in the ground state, and that's why this reaction is a thermally allowed reaction, because symmetry matches in the ground state. If C2 symmetry is maintained, as we discussed in the basic, if C2 symmetry is maintained, then then this process is a cone rotatory process, because here sign positive and negative. That means this is C2 axis of symmetry, because in mirror plane symmetry both upper lobes having positive sign. But here this is positive and this is negative. That means C2 axis of symmetry is maintained in a cone rotatory process. Okay. Now this is cone rotatory process since C2 asymmetry is maintained. Now let us discuss symmetric property. Sigma, sigma star with respect to C2 axis of symmetry. With respect to C2, sigma is symmetric, sigma star is asymmetric. So here sigma is symmetric, sigma star is asymmetric. Then psi1, psi2, psi3, psi4 which are equivalent to pi 1, pi 2, pi 2 star and pi 1 star. Asymmetric, symmetric, asymmetric, symmetric. So in this way, asymmetric, symmetric, asymmetric, symmetric, these are written here. Now psi1, psi2, psi3, psi4, psi5, psi6 with respect to C2 symmetry. So in this way, with respect to C2 symmetry, psi1 is asymmetric, symmetric, then alternate, asymmetric, symmetric, asymmetric, symmetric. So psi1 is asymmetric, okay, then alternate. So in this way, psi1 is asymmetric, then alternate, that is asymmetric, symmetric, asymmetric, symmetric, asymmetric, symmetric. Now let us see where symmetry match. Okay. Now this is asymmetric, asymmetric. This is symmetric, symmetric. This is asymmetric, asymmetric, symmetric, symmetric. Then asymmetric, symmetric, symmetric, symmetric. Okay, this matching is not possible. See here, asymmetric, asymmetric, symmetric, symmetric. But symmetric, asymmetric, this matching is not here. Then, thus only possibility is that symmetry is maintained in the first excited state. Since symmetry is maintained in the excited state, because this is ground state, this is excited state, here symmetry matches in the first excited state, that's why this reaction is photochemically allowed. So it is treated as photochemically allowed and thermally forbidden. So in this way, C2 symmetry, that means con-rotatory process, is photochemically allowed. Thank you for watching this video.